Welcome, I'm Rob Froney, and I'm here to talk about differential amplifiers. First of all, why in the world would you want a differential amplifier? Well, let me just describe one of many situations where this would be a very useful kind of a thing. Suppose you are in the university church. Down in front, the pastor is speaking into a microphone. Now, that microphone has a little difference voltage across the two wires coming out of it. But that microphone voltage needs to get all the way up to the back of the church where the amplifier for the PA system is. And so those they make two wires that go from the microphone all the way back to the church, to the PA for the church. And those two wires are very long, and they act like antennas, and they pick up a lot of noise along the way. Fortunately for us, the two wires are parallel, and they go wherever one goes, the other goes, and so they both pick up essentially the same signals, acting as antennas. So then when we get to the PA, what do we want to do? Well, we want to amplify the difference in voltages across those wires, and we don't want to amplify the voltage between either or the average voltage of those wires at all. We want to amplify only the difference. Today we're going to look at how we can use the non-inverting and the inverting amplifiers we discussed in a previous video to make a differential amplifier that will do just this for us. Let's go look and review those amplifiers. So here was the non-inverting amplifier, and the gain for this non-inverting amplifier was this guy right here, which you could write like this if you wish. Let's look at the inverting amplifier. First of all, notice that the inverting amplifier is essentially the same, except we've changed where we're putting our input voltage. We put it in down here instead of up here, and where we put it up there before, we essentially are making that voltage zero by putting it to ground. So essentially these two amplifiers look the same, except for where the input voltage is hooked up. Now the idea that this sparks is that perhaps you could hook up both input voltages, and one of them has a positive gain. That's the non-inverting amplifier. That's this guy right here. This number is always positive. And the other one has a negative gain, which would be the gain for the inverting amplifier here, which is right here. And you will also notice that the inverting amplifier has its gain and magnitude is R1 over R2, but while the a non-inverting amplifier's gain is actually 1 plus that right here. So what we'd really like is that the two gains, one be the negative of the other. Let me just discuss that and show you why that is. And in order to do that, what we're going to do is we're going to turn down the gain of the non-inverting amplifier using a voltage divider. So voltage is like height. And when you have two voltages, one for each wire, you can describe it in two ways. One for the first wire, maybe we call that VP right here. That's this wire. That's the normal way of doing it. That's the voltage between VP and ground. In other words, the height from this top line right up here to ground down here. And the other thing we'd need to describe, if we're describing it that way, to describe the other wire would be VM. That's this guy right here, which gives us the height from the lower height to ground. But that's not the only way to describe these two heights. One of them would be to, the other one, another way to do this, and the way that really matters to us, is we'd like to describe the voltage to the average of those two heights, and then the voltage, the difference between those two heights. And the reason that's important to us is because we want to amplify this V difference, and we want to ignore the V common mode. So let's look at this mathematically. I'll scoot that over a little bit so you can read it. So if we zoom in here on the equations, whoa, gotta move up here. Right here, here's the equations. So V out for an amplifier is partly due to one input, which I'll call VOP. That's due to the non-inverting input, and then we have to add the part from the VOM. This is using the superposition principle of circuits. And VOP is equal to the gain of the non-inverting amplifier multiplied by the voltage on the input of the non-inverting amplifier. That's this term right here. Similarly, the gain of the inverting amplifier is this term right here. And like I said, we could write that in terms of a difference gain right here that multiplies the differential voltage plus a gain that amplifies the average voltage, the common mode voltage. So we call that the common mode gain, and we call this guy the differential gain. Let's see how those two gains relate to the AP and the AM. So we can do that by equating coefficients of VP in both equations. In other words, if with this equation right here, if I just take and take this equation equals that guy, and notice the thing in front of VP here is just AP. So AP here equals, and what does it equal? It equals the numbers in front of VP here, which is AD plus ACM over 2. So that's how we got this equation here. Similarly, you can get this equation here for AM. And notice we wanted ACM to be 0. So if we just take and plug in ACM equals 0 right here, and we make ACM 0 right here, we get that AM equals minus AP, which equals the AP is the same as the differential gain, AD. So here's how we're gonna do this thing. We're gonna take the circuit that we had before, which was essentially this part right here. We're gonna add this voltage divider right here, and that will turn down the gain of the non-inverting amplifier to be equal to the gain of the inverting amplifier, only upside down, just with that minus sign that we just saw we needed. So let's look at the details in the mathematics here. So here's what we had before, was the A plus right here, and here's the voltage divider relationship here, and I've substituted a very cleverly picked voltage divider that has been designed just to work with this. You could solve for this R3 and R4 using algebra if you like, and that's fine, but I didn't want to drag you through that. So if you notice here, here's my voltage divider relationship right here. And if you put this together with this up here, you can come up with the AP, which is what we needed. So essentially multiplying the two gains together to get the overall gain, you will see that you end up with first of all, this is the gain of the voltage divider, and then we've got the gain of the non-inverting amplifier. Here's the gain of the voltage divider right here. And we multiplied it by the gain of the non-inverting amplifier, and notice that the way we did it, that the R1 plus R2 canceled, and the K's cancel as well. The K's I put in there because essentially there are two parameters to design a voltage divider. One is the total resistance, or the You could take any voltage divider and multiply all the resistors by any factor you like, as long as it's the same factor. If you have a 10 ohm and 10 ohm, that's going to cut your voltage in half. And if you have a 20 ohm and 20 ohm, that's also going to cut your voltage in half. So I just put that K there, and you can notice the K's cancel out. And we get exactly what we want right here, R1 over R2. That's minus the gain of the AM, which was minus R1 over R2. Now normally we don't see the circuit written that way. We normally see it written this way. And we normally pick the constant K to be 1 so that we have a nice symmetric thing on our input resistors right here. So if you notice, this top circuit here is the same as the bottom circuit. This bottom circuit is just redrawn, and we picked K equal to 1. So that's essentially how you can make a differential amplifier using the non-inverting amplifier and the inverting amplifier and adding a voltage divider. I hope this was useful.